So moving away from Antarctica to the tropics, this is the Tanzania Drilling Project, or 120 million years of exceptional fossil preservation. So the first question is, why Tanzania? Why is the Tanzania Drilling Project? Well, the story actually starts in London when the foraminiferal collection of Walter Blow, he was a famous planktonic foraminifera expert, and his collection was donated by BP to the Natural History Museum. And Giles Miller informed Paul Pearson of this latest acquisition. Paul went to look at the collections at the Natural History Museum, saw that the preservation of these planktonic foraminifera, these calcareous zooplankton, was exceptional, and it would be invaluable for taxonomic research, these samples from the Eocene. And there was also controversy at the time regarding temperature estimates for the Eocene and whether these planktonic foraminifera, their geochemistry might be altered and giving us artificially low sea surface temperatures. So that's where it all began. And this Tanzania site has been described as now as a Lagerstätten for micropalaeontological research. And normally when we think, or when I think normally of a Lagerstätten, I think of things like Burgess Shale and Messel, where we have these exceptionally preserved macrofossils. We don't normally think of microfossils needing sort of this kind of exceptional environment, because we have these microfossils are so abundant in marine sediments and in the modern ocean that we're not short of specimens at all. And we're generally getting the whole specimen preserved. But these exceptionally preserved sites allow an opportunity to look at much more of the finer details and the structures. So this is our Tanzania Lagerstätten site, which made the front of GSA Bulletin. So I'll be talking about the fossil groups of the calcareous nanoplankton. These are calcareous algae calcifying in the surface waters of the ocean. They photosynthesize, and they're present in these samples throughout, and they're beautifully preserved. And I strongly encourage you to look at the, there's also a display in the coffee area on these. And composition, the assemblage composition of the samples from Tanzania versus an open ocean site are actually very different. There's also the planktonic foraminifera, so these are calcareous zooplankton, and they're very abundant in the samples, and they appear visually different when you look under the light microscope and transmitted light. They appear transparent. They're termed glassy. You can see right through them to your picking tray. And this is particularly, we do a comparison to open ocean samples, where the specimens can appear opaque. So this is just a collection. These are the top lines from Tanzania. These are different specimens of planktonic foraminifera, and this is some specimens from a deep ocean site in the Pacific. So this is what they look. This is SEM image, and this is what the light microscope image is. So these are the Tanzania specimens with this sort of transparent, glassy preservation, and these are these deep ocean specimens with this opaque. And this becomes much more apparent when you look at a much higher resolution. So these are samples from the deep ocean. This specimen's been like etched, and it's got this overgrowth. And here we've got things that looks like this turning into a calcite rhomb in this area. And compare that to, this is Tanzania preservation. You can see this microgranular wall texture. This is a 10 micron scale bar here as well. And look at how smooth these walls are. So visually, under both the light and scanning electron microscope, the planktonic foraminifera preservation is different. So when they're well preserved, of course, that's great for taxonomic studies. It also means that we can do geochemical analyses on these specimens without having to worry about some of the consequences of diagenetic alteration. And so why are these sediments so why are these specimens so well preserved? Well, the Tanzania is a clay-rich facies. These are some of the Tanzania cores from the Cretaceous. We also have very high sedimentation rates, about 8 centimetres, 1,000 years, that'd be typical, and it's a shallow burial depth. So if you compare this to, say, an open ocean site, you would have a much more carbonate-rich facies if you're in the middle of the ocean. Sedimentation rates typically for like an ODP, Ocean Drilling Project site, would be about 1 centimetre per 1,000 years, or 3 centimetres per 1,000 years maximum. And of course, when specimens, these microfossils, travel through the water column, if you're in the middle of the Pacific, these are travelling through 3 kilometres of water, whereas the water depth here is more about 500 metres. So Tanzania Drilling Project, here's one of the rigs on site. It ran from 2002 to 2005, which mainly focused on the Paleogene, and then 2007 to 2011, which mainly focused on the Cretaceous, but not exclusively. And of course, there's much more research still ongoing on the material that's being collected. So the drilling is to get past this tropical weathering, because it's very deep tropical weathering front, to drill into this very pristinely preserved sediment, fresh sediment that's not been oxidized. So the objectives of Tanzania Drilling Project are to drill these clay stones to get these pristinely preserved microfossils for evolutionary and paleoclimatic research. So Tanzania, the area we're working in is in the southern eastern part of Tanzania. These sediments called the Kilwa group. So down here is the border of Mozambique, and that's the border with Kenya. Here's some of the major towns with some of the drill sites. And there's been 40 shallow boreholes drilled to date, to about 150 metres depth. And this has recovered successions from Albian to Oligocene. And these are all the cores drilled to date, numbered from 1 to 40. This is time here from the Albian through into the Oligocene. Compositely, we actually have a very good coverage through this interval with some minor gaps. And these are all drilled into these clay-rich facies. There is occasional sands and limestones, and we do get transported shallow water debris. The paleolatitude's about 20 degrees south. As I said, the water depth's about 500 metres. And all these sites have this exceptionally well-preserved carbonate, but also organic carbon. So the aim, one of the aims was to drill into these, to recover some of these classic or very critical climate intervals, including what Peter was just talking about, this Eocene-Oligocene glaciation, the Paleocene-Eocene boundary, KT boundary, and the Cretaceous OAE intervals. But finding the best locality to drill for these is actually quite difficult. This is the field area for a start is very large, and the geological mapping of this region is prior to this was actually very coarse. So we're covering a very large area which has a very not a very expansive road network. This is a typical field site. So we're looking for outcrop. And of course, the whole area is extremely remote. Here's a good outcrop, quite a large outcrop. Here's a smaller outcrop. With some of the locals. Here's an elephant, a spider. And we're camping in the field during the drilling. So we're on site. Of course, there's no electricity, there's no internet, there's no email. This is our convener cooking me dinner. And so the drilling and all the operation in terms of the core description and the sampling all took place on site. So here's a drill site here with here's one of the sampling stations. So here's the sample descriptions of these clay-rich facies, these cores. So sampling and the core descriptions taking place as the cores come up. This is the micropalaeontology preparation area and some on-site micropalaeontology. So, of course, we wanted to know exactly the age of the material as it was being drilled. So funding from this came through a series of NERC grants. So it started with a NERC Small grant and some NERC Standard grants, National Science Foundation grant by Brian Huber. We also have an integrated ocean drilling proposal in the system. And this funding was also supplemented by things like Enterprise Island and People's Fellowships and from the Royal Society or from NERC to supplement just the, not just the drilling, but also the logistical support for travel. And it's an international team of scientists from 8 different countries. So, of course, the logistical support on the ground from Tanzania was also very important. And yes, so this is Joyce Singano. She's at the Tanzania Petroleum Development Corporation. She did her PhD at UCL. And so working with a research collaboration with people in Tanzania and also helping with the logistics with the red tape and the vehicles and also the archiving of the core also took place through the Tanzania Petroleum Development Corporation. So the core recovery is about 90%, particularly in the times we had wireline logs, like wireline drilling, but the lack of borehole casing did prevent the recovery of some of our critical intervals like Cenomanian-Turonian boundary or the Palaeoclimate boundary. So talking about the evolution of the microfossils and what this exceptional preservation can tell us about microfossil evolution. So I'll start with the calcareous nanoplankton. And this group's been around since the Triassic. They're really abundant in the modern. Here's a bloom of Emiliana huxley in the English Channel. And of course, the chalk is predominantly made up of these organisms. So you'd think, as we have billions of specimens and their global distribution, we would have a complete fossil record of these things. Apparently we don't. There's, in the modern, apparently 90% of species that are, only 90% of species they're greater than 3 microns in size. And 20% of those smaller than 3 microns only have fossil records. So we do lose quite a lot in the modern to sediment deposition. So the smaller taxa aren't being preserved. So this is Paul Bowen, and he's been doing SEM and light microscope imaging of the material from Tanzania. So this is just this is play on an SEM stub, and I'm just going to focus in on, so the scale bar here is 100 microns, but I'm just going to focus in on this. And so the scale bar now is 5 microns. You can see that it's beautifully preserved calcareous nanoplankton, and all these really fine structures are being preserved. And some of these specimens are very small, typically smaller than 3 microns. So this is much smaller than some of the things that are being preserved in modern sediment. And this is just a comparison to the Danish Cretaceous chalk, where you've got the scale bar here's 5 microns again. So we do have, it's mainly these larger specimens that are being preserved, and then we have all this micrite, which may well be, well, in the past would have been calcareous nanoplankton that have now been dissolved and disaggregated. So here's another specimen. This is from the Eocene, Tanzania. And it's just highlighting some of the major groups. We have all these small, delicate forms that are being preserved. And many of these are actually extant groups that don't previously have a fossil record. So we're showing their fossil record for the first time. So of course, if normally we're losing all these small and delicate forms, what kind of implications does that have for our evolutionary understanding and our palaeo-ecological reconstructions? Well, it has a big implication. This is time from the Cretaceous Paleogene through to the Oligocene, and this is the species richness of a bunch of different sites. These green and bluey dots are from the Pacific Ocean, and this sort of shading represents a sort of global compilation of species diversity. and these red squares are the data from Tanzania. So the species richness in these Tanzania sediments is much higher, almost double what we're finding in the deep Pacific Ocean. So there's a huge diversity loss occurring in these deep sea sites. So far there's about 150 new taxa have been named from Tanzania, and it seems that 50 to 90% diversity loss is not unusual in these sites, and it really underlines, as well as the foraminifera, which we have, we can visually see that the preservation is different between carbonate-rich and clay-rich facies. Also, this clay has a very taphonomic signal that we can detect in the diversity of these calcareous nanoplankton. So just focusing on some of the groups, this is an image that's also on the display outside. This form, Gladiolithus, this is a modern nanoplankton genus that actually lives quite deep within the photic zone, and it's found in the water column, but very rarely found on the seafloor. But we have it in Eocene sediments, so these are the same these elongate elements, and it's indistinguishable from the modern taxa. And this group has no pre-Quaternary record, so we're extending the range back of the origination of this taxa actually back to at least the late Paleocene. And in terms of the ecology, it's quite exciting because it suggests that this form that lives in this deep photic niche probably occupied that same habitat back to sort of Paleocene. There's also these forms. They have no previous fossil record. These are from the modern, and here they are in the Eocene, and here they are in the Cretaceous. So we're extending the range of all these modern taxa back through time. So this is the chart going from 90 million years ago to present day. These are different genera. The green represent their modern known distribution, and these big orange bars represent how far we're extending back their radiation. So we're extending the radiation back not just hundreds of years, but millions of years. So in terms of understanding the radiations of these groups, then the Tanzania material has been incredibly important. And there's also extensive ongoing work going on in the Cretaceous, on the foraminifera and the Nano Fossils, and Jackie Lees and Stuart Robinson are here to, if you want to discuss them and also see the displays outside. In terms of the preservation, what we can do with the geochemical signals is because we have such good preservation, we can actually do geochemical analysis on the planktonic foraminifera without this consequence of diagenic alteration. We also have the organic rich sediments to do some of the proxies that Peter was previously mentioned, like TEX 86. So one of in terms of paleoclimate, one of the big questions to address was this what was known as the cool tropics paradox. And for the Eocene, which Peter pointed out, this time with high CO2 levels, it's much warmer than today, and there's abundant evidence from both the floral paleontological record and the faunal record that high latitudes were very, very warm. But the oxygen isotope data from planktonic foraminifera suggests that the tropics are actually cooler in this greenhouse climate. So here's the Paleocene through to the Oligocene. These open circles are the benthic foraminifera oxygen isotopes and their translation to temperature. And then these filled circles are the planktonic foraminifera oxygen isotopes, both from Pacific open ocean sites. So the sea surface temperatures are about 20-25 degrees, which is cooler than they are in the modern at these sites, and much cooler than we would expect them to be in the Eocene, which is a greenhouse world. So to test this cool tropics, you can run these pristinely preserved planktonic foraminifera to see if their oxygen isotope signal and their translation to temperature is warmer or consistent with this. And they're much warmer. The red is the planktonic foraminifera option isotope temperatures, and the yellow is this TEX 86 temperature proxy. And we get temperatures of about 32, 34 degrees, quite consistent through the Eocene. And they're not showing this cooling trend in sea surface temperatures that's shown on these deep sea sites, and then which suggests that this is all an artifact. It's not that the Pacific was much cooler than the Indian Ocean. This is all an artifact of diagenetic alteration and of running these opaque, recrystallized planktonic foraminifera. We also drilled some significant boundaries, such as the Paleocene, Eocene, and the Eocene-Oligocene boundary. I just wanted to show some data from the Eocene-Oligocene, which was drilled in this place called Stakishari. And as Peter pointed out earlier, this Eocene-Oligocene interval was a time of major ice growth on Antarctica. We've got global cooling. In terms of the paleontology, there's also extinction both in the marine and terrestrial records through this interval. So this is me sat on the Eocene-Oligocene boundary, which is actually exposed in this very narrow gully. And we know it's the Eocene-Oligocene boundary because the marker species is this form called Hankinina, and that goes extinct. That marks the EO boundary. So we find Hankininas in these sediments, but not in these sediments. So we put the rig up here to drill through this Eocene-Oligocene boundary section. So here's the rig. Here's some drilling in action. And because we have this kind of unique snapshot into the assemblages at this time, we know they've not been altered or been dissolved, we can look at the biotic response across these critical intervals without worrying that that certain delicate forms have been dissolved. So we can link the biotic changes to the climatic changes. So we have, so in terms of the biota, we do have winners and losers over this interval. So this is time on this axis. The red marks the Eocene-Oligocene boundary, and these are just different species of planktonic foraminifera. And the losers are the things like the Hankinids, whose extinction marks the EO boundary, and also these forms, these Turboretaliids, which go extinct just before the boundary. But there's other forms that go through this, and they love this time interval. This thing, Amphiapertura, occupies about 50% of the assemblage. So we can look at diversity trends through these groups and how it relates to climate change. So that was the forams. This is the Nano Fossils. This is Dunkley-Jones et al. And the red line again is the Eocene-Oligocene boundary. So here are the losers, these forms here, which decrease in abundance, and these are the winners, these taxa that increase abundance over this interval. So this is really the first time that we can do this, because in deep sea sites, many of particularly if we're close to or below the CCD, these microfossils will be dissolved. So we're able to link the climatic and biotic change. A very confident place where the extinction of the Hankinina is, and that's important stratigraphically to link these very detailed isotope records that we now have through this interval to the stratigraphic records. We can also, we've published on the temperature change and the ice volume change through this interval, and also changes in PCO2. There's also the Paleocene-Eocene boundary. There's lots of work ongoing for this interval where we have great climatic warmth and a big carbon isotope excursion. So the TDP has been incredibly successful. It's about 30 publications to date, including publications in Nature and Geology, EPSL. And there's much more work that's still ongoing. So it's an incredibly successful program through international collaboration involving just the paleontology and the geochemistry. But it was these small skid-mounted rigs, maximum penetration about 150 metres. Generally, we don't have wireline logs. The recovery is variable. And the cores are too thin to be able to slice in half and have an archive and a workive half. So we have to do whole round sampling. So we now have a proposal to go offshore Tanzania for the Tanzania Offshore Palaeoclimate, or TOP. So this is a proposal with the Integrated Ocean Drilling Programme on the Georges resolution. to drill these same clay-rich fashy sediments offshore to get a continuous Cenozoic record. So we already had a site survey in 2009 to find the best places to drill. We also did box and piston cores, and here are some of the planktonic foraminifera. These are from the Pliocene, about 4 million years old, and you can see all the spines preserved in the umbilicus in these regions. Look at these incredibly smooth walls, the scale bar is 10 microns. So the preservation in the offshore fascies is just as good as what we're finding onshore. So we have the opportunity to get the younger part of the record as well, of drilling the Miocene and the Oligocene. And because we're very close to continental Africa, by drilling offshore, we could also link the terrestrial records to the marine records. And this is particularly important because this is East Africa and the hominin evolution taking place at this time. And we would expect there to be spores and pollen, and we can reconstruct the hydrology from the terrestrial records by looking at this very close marine record. So the objectives of drilling for the offshore is to look at temperature change through the Cenozoic, through these multiple proxies, to reconstruct Cenozoic carbon dioxide levels using both the inorganic and organic proxies, the evolution of the biota and the response to climate, the connection with the terrestrial African sections, looking at the vegetation, continental air temperatures, taking advantage of these new organic biomarkers, a relationship to hominin evolution, and also enhance the chronology of the Cenozoic using the microfossils and magnetic. So many thanks to the TDP team, some of which are in the audience and up on the screen here. And just to sum up, as Tom mentioned earlier, these are small fossils, but they have implications for big paleontology. And it's this exceptional preservation that provides these insights into the nanofossil diversity, the foram evolution, and also the paleoclimate and the link between the Bartic and climatic change. But yes, there's plans for the future.